All right. Hopefully everybody enjoyed the somewhat short homework assignment this week. I mean, I think that was about as short as I could make a homework assignment. Um, uh, if you remember, I said that this homework assignment you could probably do on 2 lines of notebook paper. Hopefully everybody found that to be the case. Um, I want to just jump right in today, and I want to talk about beams. We kind of need to set the stage for the rest of the semester in regards to beams, and one of the things that matters with beams is bracing, okay? And what is bracing? What is the role of this term called LB, which we're going to talk about today? And I want to get into the first of 2 types of beams that we're going to handle for this semester, and that is a continuously braced beam. Later on, we will look at a discretely braced beam. This real quick. So let me just jump right into it, and let's start off by talking about beam capacity and the role of LB. Okay, now you haven't heard of LB yet, and that's fine. That's the point of today. But let's just take it one step at a time. Let's start off with beam capacity. Now, after the lecture from last time, everybody should be pretty clear that the maximum possible capacity of a beam is its plastic moment, or Fy times Z, that term, the plastic section modules. You all just had a homework assignment on how to compute Z. So everybody in here should be pretty comfortable with this term. Now, I want to be crystal clear. This is not the maximum capacity of every beam. I'm not saying that every beam has a capacity of MP. What I'm saying is that every beam has a maximum possible capacity of MP. Okay. The problem with what makes beams complicated is buckling. Okay. Now, if you remember columns, if you have a column and you take a column and you load it in compression, it buckles, right? Things in compression like to buckle. Well, beams experience compression too. You take a beam and you bend it, and part of the beam is experiencing compression, part of it isn't. If you have a beam and you bend it, like smiley face bending, the top of the beam experiences compression, the bottom of the beam experiences tension. So part of the beam that is experiencing compression, it wants to buckle. Beams have a very specific way that they buckle. They buckle in a way where they actually sort of kick out and twist. It's called lateral torsional buckling. We'll talk about lateral torsional buckling later. I'm not really concerned so much about defining that now. All I want you to understand right now is that beams do want to buckle. And also, like columns, beam capacity is a function of its bracing, of the braces that frame into it. Okay. This box over here, this gray box here in the corner, this is deceptively probably one of the most important statements regarding beams, period. There is a difference between how long a beam is and the distance between its braces. Okay. And don't worry, I got some images that sort of clarify this here in a second, but I want you to make sure that you're aware that there's a difference between how long it is and its unbraced length. And so LB, I might call it instead of saying LB, I might call it its unbraced length. Okay, but let's walk before we can run. All right, let's talk about bracing. Okay, so LB, like I said, this term LB is the distance between braces, or it's commonly referred to as the unbraced length. Okay, and so what do I mean by a brace? Okay, let me stop sharing so that everybody can see this. All right, can everybody see me on the camera? Is that showing up on screen? Can everybody see me? Yes. Okay, good. Okay, so here I have a beam, okay, and let's just say for the sake of discussion that this beam is like, I don't know, 3 feet long. I know it's a little shorter than that, but let's just say it's 3 feet long, okay? A brace is any device or any structure where its purpose is to prevent the beam from moving left to right when it wants to buckle, okay? So in other words, here's the beam, okay? Any device that prevents it from going this way laterally, that's going to be a brace, Okay, so let me sort of pull share the screen back because I want everybody to see this. Um, okay, everybody should see the screen now. So I got a couple. I've got a couple images here that I kind of want to show you. Let's look at this image over here on the left. This image over here on the left is looking at a bridge system. So in this bridge system, there are 4 beams. The beams are the elements that are going in and out of the screens. So that's a beam right there, this long element. This element right here, that's a beam, and this is a beam. And in between those, you should see these little, like these truss-looking things. They look like there's horizontal elements, and then they look like they got a letter V in between them. Those elements are intended to prevent the beams from buckling at that point. At that point, they're preventing the beams from moving laterally. So these elements, which we call these cross frames, sometimes they're called diaphragms, but cross frames in this system, those cross frames are acting as braces for this beam, okay? So that's an example of a brace. Another example of a brace is just another beam framing into it. So over here on the right, I have a structure that's being erected. So you should see we've got this element right here, this horizontal element, and we've got this iron worker that's sitting on the element. If you look behind the beam, see this element that's being lowered with a crane, this beam. So here's the beam, or here's the crane, and the crane's lowering this, and you can see it's being connected here. Well, on the other end, this beam that's in the background would frame in right here on the girder, the element that the iron worker is sitting on. So this beam would actually serve to brace this girder right there. And so that would be a brace for that beam. So cross frames can serve as braces, and other beams framing in can also serve as braces. Those are probably 2 of the most common bracing elements that you see in structural engineering are, cross frames and other beams. Again, very, very, very critical, and I hope everybody sees that. Now, let's talk about some notation. So later on, when we denote this, we'll look at bracing scenarios, and we'll look at it like this. So for instance, let's say I have a beam that's simply supported and it has a uniformly distributed load on it. This is what I was meaning when I was saying that there is a difference between how long the beam is and its unbraced length. So to keep it simple, we might say that this beam is 30 foot long. But this dimension here between the braces, this is 10 foot, and this is 10 foot, and this is 10 foot. So there is a difference between a 30-foot long beam and its LB being 10 feet. Okay, I want everybody to make sure that they're crystal clear about the difference between the length of the beam and the LB. Now, what a brace serves to do is quote unquote strengthen a beam, because the idea is that as the distance between the braces goes down, the capacity of that beam goes up. Okay, so it's like a column. The longer a column gets, the more slender it gets, and the more slender it gets, the more it wants to buckle. And it's the same thing with beams. As that unbraced length gets longer and longer and longer, not the total length of the beam, but the unbraced length. As the unbraced length gets longer and longer, that unbraced segment gets more and more slender, and it wants to buckle. And vice versa. As the unbraced length gets shorter, the beam gets stronger. But again, no matter what, the capacity can be no larger than MP. Okay? So what we're going to do to start out beam analysis and beam design in this class is we're going to assume that the beam is continuously braced. In other words, you could think about it as having like an infinite number of braces coming in. So like this slide here has what, 4 braces, like one here, one here, one here, and one here. Well, imagine that there's like an infinite number of braces that are preventing that beam from moving left to right. Another way of looking at it is this would be a scenario where if it has an infinite number of braces, the LB value is 0. We're going to handle LB equals 0 first, and then later on we'll look at, well, what if LB isn't 0? What if there is a distance between braces? Now, I do want to be clear that just because I'm saying that LB is 0, I don't want you to think that this is just a mathematical abstraction, that never happens in real life. It actually does. This is a real world example of a case where LB equals 0. What we have here is a scenario. Here's the beam. So here's the beam, and the beam's going like this. Typically, when we cast concrete decks on top of beams, and this is true whether or not we're looking at buildings or we're looking at bridges, but we tend to do this through the use of shear studs. So we'll have these shear studs welded to the top of the beam. They look like really big nails that are kind of welded to the top. And then when you cast the concrete surrounds these nails, and when the concrete cures, it forms a bond with those nails. We call them shear studs. And so when you load the beam, the concrete is actually along the entire span, preventing that beam from moving left to right. So it's sort of providing a brace continuously along the beam, hence a continuously braced beam. So this is going to be sort of the first scenario that we consider, and that's a continuously braced beam. And we do that because it's the simplest case. Later on, we'll look at discretely braced. But again, you got to walk before you can run, so we're gonna take our time with that. Now, okay, so hopefully everybody's good with that so far. Again, if you have any questions, please, throw them out in the chat. I want to make sure that we're clear on this. Whenever you analyze a steel beam, and by analyze I mean verify that the beam has adequate capacity, that it is performing adequately, there's three things that you need to assess. You need to make sure it has adequate moment capacity. You need to make sure it has adequate shear capacity, and you need to make sure it has that it meets deflection limits. Okay, so this, for those of you that are in concrete design, this is sort of the same thing in concrete design, because we had to make sure that Phi-Mn was greater than or equal to Mu. We had to ensure that the shear capacity was enough. If not, you had to provide stirrups, and then it has to meet deflection limits. We're talking about deflections right now in concrete design. And keep in mind that when I say that there's three conditions that beams need to meet, I'm not talking about whether or not the beam is braced continuously or discretely. All beams have to meet that scenario. It has to have adequate moment capacity, adequate shear capacity, and meet deflection limits. Now, a couple of notes. We're going to cover the shear capacity later. For now, we're just going to use a design aid to look it up. But what we're going to find when we look at shears, and this is true of shears in building design and building beams, when you're looking at steel beam design and you're looking at shears, they end up really not being that big of a deal. The way that we manufacture rolled beams, like rolled W shapes, they tend to have like just loads and loads of shear capacity. Shear tends to not be a problem. The moments and the deflections tend to be what govern the design. Shear kind of ends up being an afterthought in steel beam design. Also, one other thing, deflections in here are much more straightforward than they are in reinforced concrete. See, in steel design, we don't have to worry about cracking or effective moments of inertia or anything like that. So all that staged loading stuff in concrete design, we really don't have to worry about it in steel design, because there's no cracking. The beam behaves like a rubber band across the board. So the moment of inertia doesn't change. And so since the moment of inertia doesn't change, we can just compute everything directly. It's a lot more straightforward. Now, Phi-Mn, so if you have a continuously braced beam and the beam is not going to buckle, you don't have to worry about that side-to-side buckling or anything like that, then its moment capacity is just Fy times Z. It's just the plastic section modulus, or the plastic moment, the Fy times the plastic section modulus. For Phi values, Phi is 0.9, so Phi for beams. Now, I want everybody in their manual to turn to this table. Okay, this is table 3-2, and it starts on page 3-19. Okay, I'm going to give everybody a sec to turn to this, because this is an incredibly important table. For beams, there are two design aids that we are going to use very extensively. This is one of them. We'll probably be using this aid between now and the end of the semester. We'll be using it like every lecture from here on out. So this is definitely one that you will want to tab, which is table 3-2. I probably will not call it table 3-2. I'll probably call it the ZX tables because you see up top, there's a big ZX at the top. Now, again, it's table 3-2 on page 3-19. It should look something like this here on the screen. Now, I want to be clear. There's a lot of stuff in this table. There's, if you look, there's like FEMPs, there's FEMRs, there's this BF term, LPs and LRs, all sorts of stuff here. When it's all said and done, we will know what all of these terms are. Okay, we'll know what they all are. But for now, the only thing I'm really interested that everybody understands is obviously what ZX is, what FEMP is, and then I don't know, maybe the shear capacity. I mean, there's the moment of inertia here, which I'm sure everybody's familiar with, but really what's supercritical is the moment, the FEMP and the FEVN. Now, again, there's a lot of values in this table, but what should we table this at? I would just call it ZX tables, just ZX. In fact, here, I don't know if you all can hop back and forth on my screen, can't you? You all can pull my camera up, right? Like you can click down below and pull mine up. I think, isn't that how that works? All right, so hold on. I don't know how legible this is going to be, but mine, let's see. Yeah, I don't know if you can see that. It just says ZX. I just call it ZX tables. A couple other points worth mentioning. So right now, again, I just want the FEN values. When it's all said and done, we'll know what all these values are. Another thing, the reason why we call this the ZX table is because if you look at the columns, if you look at the way they're organized, they're actually organized by their ZX values. So if you look, like here on the slide, it's like 464, 442, 437, 436. I mean, it's literally just all the beam shapes sorted by ZX, okay? So as a result, sometimes it can, like if you're analyzing a particular beam and you're trying to find like the W14 by 233, it sometimes take you a little while to find it because, you know, it's sorted by ZX. Also, if you look at the table, you will find that they are grouped. Like there'll be like 5 shapes and then 7 shapes and then 8 shapes and then 2 shapes. And if you look, they're always grouped, but the top row is bolded, okay? I wonder why that section is bolded. Don't worry, on Friday we'll discuss that. You could probably by observation figure it out, but we'll look at that on Friday. Don't worry, you'll understand why. Will FY always be 50 so these tables are accurate? Matt, you stole that right out. I was just getting ready to talk about that. Got some precognition there. He asked about FY is 50 KSI. It is correct that these tables are written based off of FY equals 50 KSI. That doesn't mean they're completely useless if it's not 50 KSI, but that'll be a little clearer on Friday because in design mode, you could still design if 50 isn't KSI. You just kind of have to take an extra step, but that'll become clear on Friday. Moving on, unless anybody's got any questions, again, don't hesitate to interrupt me. I want to make sure I'm answering everything. I want to talk about limit states. For those of you in concrete design, I shamelessly pulled a lot of this from a lecture the other day, but everything still applies. Up until now, we've been considering what are called strength limit states. And so strength limit states are things like the moment capacity, the shear capacity, and whenever you're dealing with a strength limit state, it's intended to ensure the safety of the structure. So whenever you use load factors, you know, like your 1.2 dead, your 1.6 live, that's what you're looking at. You're looking at structural safety. So you always factor the loads. However, with service limit states, you use service loads. You do not factor the loads. And the reason why that's relevant is because we're looking at 3 things. We're looking at moment capacity, shear capacity, and deflections. Whenever you're looking at deflections, you do not factor the loads. You just use the raw loads. It's because we're not dealing with structural safety. We're dealing with issues that if you fail to a service limit state, it doesn't mean that the building's going to fall down and kill people. It just means that it's not performing the way that you wanted. So you still need to check it, but it's just not as big of a deal. So 2 takeaways. When you're looking at deflections, no load factors. Do not use load factors. And 2, again, I mentioned this before, but steel beams don't crack. They don't experience cracking where the moment of inertia changes. As a result, deflections are much more straightforward in steel design than they are in concrete. No cracking, no IE, no stage loading. You can just compute your live load directly, live load deflection directly. I do want to point your attention to this. I've got a typo. It says table 3-2 when actually it's table 3-23. That's 3-23. Sorry. So table 3-23 on page, starting on page 3-28. I haven't pointed your attention to this in steel design yet because we haven't needed it until now. But for those of you that are in concrete design, we've sort of been using something very similar to this the entire semester. The shears, moments, and deflections for very typical loading scenarios are also in the steel manual. It's in the back of the beam section. It starts on page 208. I have that tabbed as well, and I'll show you here on the camera. Hold on. I kind of just called that VM delta, just shears, moments, and deflections. You all can call that whatever you want, but it's just your beam analysis tool. So, for instance, simply supported beam, uniformly distributed load, the maximum moment is WL squared over 8. Your maximum deflection is 5 WL to the 4th over 384 EI. Like, I mean, and there's also other load cases as well. Now, also, don't forget, if you remember in structural analysis when we computed deflections, we always had to throw that conversion factor of 1728 in to convert our units because our member lengths are in feet, but our moments of inertia are in inches. So you have to make sure that the units are consistent. So you just got to be consistent there. Okay. Before we get into our example today, are there any questions? We've had a couple, and I want to make sure that I'm answering these. This is going to be pretty straightforward today. All right. Let me get somewhat set up here. Give me a second. I labeled it as VM delta, and it's hold on, it's 3-23, not 28. But yeah, I called it VM delta. Again, you can call it whatever you want, but it's just I called it VM delta. Shears, moments, deflections. All right, I'm gonna go ahead and just jump right into it. Again, if you all have any questions, just please throw them in chat. All right, we're gonna analyze this beam and we're gonna verify its performance. So we're gonna say we've got a W21 by 62. We're gonna say it's grade 50 steel, A992, so FY is 50. It has a dead load of 1 kip per foot and a live load of 1.5 kips per foot. One thing I wanted to mention, I had uploaded these slides yesterday, and I said that the live load deflection limit was 450, but I did some tweaking on the example today, and I changed that to 400. So if you downloaded the slides, that's different. But then again, I'm going to re-upload the slides after the lecture anyways, because I want to fix that this typo. I want to fix that. So I'll upload the slides here in a bit. All right. So we're going to look at this beam, and we're just going to verify its entire capacity. We're going to assume it's continuously braced. It's 32 feet long. Now, right here, the dead load shown does not include the self weight of the beam. We're going to have to calculate. We're going to have to account for that. So just want to make sure everybody's clear on that. All right. So let me stop sharing. All right, so here's the problem that we're looking at. I said it's a W21 by 62, and it is a grade 50 steel. Again, I want to make sure that everybody's involved in chat, so help me out with something. We're going to need some properties for this W21 by 62. So you all should be able to find this in the very beginning of the manual, like the table 1-1. I want you to help me out. What is ZX for a 21 by 62? And what is IX for a 21 by 62? So somebody tell me ZX. $144, and the units? Yep. And IX, somebody else? 1330. And inches to the fourth, exactly right. Now, here's something that you also need, but you don't need to look it up. Somebody tell me, what is the self-weight of a 21 by 62? Don't need to look that one up. Exactly right. It's a 21 by 62. It's 62 pounds per foot. Okay. We need that quantity to do our analysis. Okay. All right. So our moments and shears. Now, we have a dead load of 1 kip per foot. We have a live load of 1.5 kips per foot. And we have a self weight of 62 pounds per foot, or 0.062 kip per foot. And this beam has a length of 32 feet. So because everything is simply supported, it's a simply supported beam and a uniformly distributed load, we can handle these pretty straightforwardly. Let's start off with the dead load moment. So the dead load moment in this case is WL squared over 8. So 1 kip per foot times 32 feet squared over 8. And when you plug and chug 1 times 32 squared over 8, that comes out to 128 foot kips. Now, that is the formula for the moment. I want somebody to tell me what's the formula for the shear. What is the maximum shear on a beam with a simply supported, or what is the maximum shear on a simply supported beam subjected to a uniformly distributed load? It's not WL squared over 8. That's the moment. I want somebody to tell me that in chat. If you have a simply supported beam and a uniformly distributed load, what is the maximum shear? Again, you can go to table 3-23. All right, so Austin's answer is that's the equation for shear. So now I want to mention something. So if you look at the table, this is something you got to be careful with. It says W, like Austin wrote W 1/2 minus X, that one's actually an L. It looks like a one, I know, but that's the length. But that is the equation for shear. So that would be shear as a function of X, but there should also be a listing for the maximum shear. And what Mr. Rain said is correct. The maximum shear is WL/2. So that's 1 kip per foot, 32 feet over 2. And so that is, oh goodness, 16 kips. All right. Does everybody see the difference between the equation for shear and the maximum shear? Yeah, if you look at the shear diagram, you can see how the V, the R, that's the maximum shear. All right. Now, that's for the dead load. Similarly, we're going to have this for the self weight and this for the self weight. And then also for for the shear. Now, it's literally the same calculation, just different loads. So instead of 1 for the dead load, use 1.5 for the live load and 0.062 for the self weight. So I'm just going to write these values out. For the moment, or for the self weight, this is 7.936. And this is 0.992. This is 192. This is 24. That's 16. So therefore, now that we have the dead load moment, the live load moment, the self weight, and then all the shears associated, we can calculate a factored moment and then a factored shear. So let's do the factored moment first. So it's 1.2 times the dead plus 1.6 times the live. Well, what about the self weight? Well, the self weight is a dead load. It is a permanent load on the structure. So I'm going to treat it as a dead load. So and so that's going to come out to be, when it's all said and done, we'll say 470.3. That's close enough. And then similarly for the shear, that comes out to be 58. If you want, for this step, MU is foot kips, and then VU is 58.8 foot kips. All right. I'm going to give everybody a sec to catch up. Just a heads up, that connect is a bit poor, so I'm going to send a message in on that. Oh, goodness, go away. All right, can everybody see me and hear me? Could somebody respond in chat? All right. I apologize for that. I don't know what's happening. I think it's I don't know if it's the weather or whatnot, but I've been having some intermittent connectivity today. So let me go back to the example. Sorry about that. Okay. All right. So this is where we left off. So we should all be here. Did anybody have any questions up until this point? I'll give everybody a second. All right. Okay, so let's go ahead and chug through this. So first thing we're going to do is, so what we've done here is we've done the analysis. So now I want to look at the capacity. So first off, let's compute MP. So MP is Fy times our Zx quantity. So again, that's just from the lecture last time. So that's 50 KSI, and that's Zx was 144 cubic inches. And so if you chug this out, 50 times 144, you're going to get 7,200. And then now here's the thing with units. We've got KSI times cubic inches, so that's inch kips. Okay. Now, MP, we're ultimately going to want that in foot kips. Now, if I've got inch kips and I want foot kips, what do I divide it by? I'm going to engage chat on this one. Exactly. So 7,200 divided by 12, that is 600 foot kips. So therefore, now we're dealing with a continuously braced beam. So maybe I'll say for a continuously braced beam, phi mn is just phi mp. So 0.9 times 600. And so phi mn is 0.9 times 6, or 6 times 54, so that ends up being 540. Okay. Now, First off, that's a really simple calc. It's actually not totally necessary if you're able to find it in the ZX table. So what I want everybody to do is this. I want everybody to go to the ZX table. So I want everybody to go to table 3.2. And first thing I want you to do is I want you to find the section that we're looking at. Remember, we're looking for a 21 by 62. Now, while we're there, I want somebody to help me out with something, okay? So I want you to find for a W21 by 62, I want you to tell me two values for this one. First thing I want you to tell me is this. That's the shear capacity. So somebody tell me for a 21 by 62, what is the shear capacity? Now, again, it can take a little while to find it. My advice is this. The Z value was 144. So go off of a Z value of 144. I think you might be looking at the wrong set. Oh, you're looking at the green numbers. Remember, we always look at the blue numbers, John. The 168, that's ASD. We always look the blue ones. So VVVN is 252. There you go, 252 kips. Now that there's that, I want somebody to tell me something else. Tell me what this quantity is. $540, exactly. And that's in foot kips. And if you notice, those match, okay? And they match because, I mean, it's just, PMP is just a plastic moment. The reason for the X is because it's being bent about the X axis. So that's all that is. So yeah. So phi MP about the X axis is 540 foot kips, which is exactly what we found. So you technically don't even need to compute MP. I just want to make sure that everybody's comfortable with just looking it up. But then there's also the shear capacity. Okay. So to summarize the capacity, let me show you something. All right. So therefore, so we got a phi MN of 540 foot kips. Now, remind me, what was MU? Somebody in chat, tell me, what was MU? $470.3. So does that mean that this is a safe design or an unsafe design? Is it good or is it bad? Tell me, what's the deal? It's good, exactly right, because it can hold up 540 foot kips and it's only being subjected to 470.3. So that is okay. That is good to go. Now, what about the shear? The shear, we had a capacity of, what is that, 252? Now, what was the load? Somebody help me out. What was the load? I forget. 58.8. So not only is that good, but that's really good. I mean, look at those numbers. Like, it can hold up 250 kips and it's only being subjected to 60. That happens with shear. So don't freak you out. Shear does that. With shear, you will tend to find you have way more capacity than you need. That happens. In fact, if we have time, depending upon our online lectures, shear is the very last thing that we'll cover for that very reason. For buildings, it tends to not be a big deal. For bridges, that's a different story, but for buildings, just tends to not really matter all that much. Now, last thing that we're going to look at is deflections. And load deflection check. In structural engineering, most of our deflection checks are related to the live load, because with dead load, we can sort of get around it. Like, for instance, in steel design, you can actually take your beam and permanently and physically bend it upwards so that the dead load deflection doesn't have an effect. So, for instance, let's say you do the math and it's going to deflect, I don't know, 2 inches under the dead load. Well, we'll actually take the beam and physically bend it upward 2 inches so that when you put the dead load on it, it sits flat. That process is called cambering. And so in steel design, and even in concrete, there are ways to get around the dead load deflection, but not really so much the live. Hence why a lot of our deflection limits are related to the live load. Now, for the deflection check, we're going to need a few quantities. We're going to need the live load, which was 1.5 kips per foot. The beam itself is 32 feet long. We need the E value for steel, which hopefully everybody can recite by memory, is 29,000 KSI. 21 too many O's or zeros. And we need the moment of inertia about the x-axis, which we looked up at the very beginning of the problem, and that's 1330. And so our live load deflection is, for a simply supported beam and a uniformly distributed load, this comes from table 3-23 that we just looked up, 5WL to the 4th over 384 EI. And so we got a big fraction. I can do better than that. And then 5 times 1.5 kip per foot times 32 feet. Don't forget to raise that to the 4th. And then remember, when you use conventional units, you got to throw in that conversion factor of 1728 to get that answer in inches. So I'm going to give everybody a sec to check that out. I want to see what you all get. I want to make sure you're comfortable with this. .917. That's exactly right. I think I got 918, but 917 is close enough. I know it's 11:50. I'm going to go for a couple more minutes. I apologize because of my internet connectivity. Well, I'm going to change it then. I'm just playing. All right. So delta limit, remember this problem had a maximum deflection limit of L over 400. We're going to talk about on Friday where those deflection limits come from in steel design, because it's not as straightforward as it is in concrete design. So the limit, or the length is 32 feet over 400. And then don't forget, we kind of need to convert that to inches too, so that we get limits that we can, compare adequately. So 32 times 12 divided by 400 ends up being 0.96 inches. So our live load deflection is 0.918, but the limit is 0.96. So since it is deflecting less than the limit, this is also okay. All right, I'm going to give everybody a quick sec to see if you have any questions, and then I'm going to pull up the homework real quick. All right, let me stop this sharing and let me share. What table did delta L come from? That came from table 323. The same place that we found the shears, the VM, the same place. All right, this is your homework assignment for Friday, or between now and Friday. It's very similar to what we just did. It's just a different analysis case. So we have a 24 by 68. It has a deflection limit of L over 180, so the deflection limit's a little different. This first hint actually really doesn't apply so much if you follow what we just did, because I made it a point to handle this problem like this, to compute the dead load and the live load separately. I should, I guess, also include the self weight, like the M naught and the V naught. You do need to account for that. But then again, the only dead load, where it says here, the only dead load present is the beam's self weight. So in this case, MD and M naught are the same, and VD and V naught are the same. You need to compute everything separately, but I did that in this example, so if you follow that process, you should be the same. But the big thing to note is that this is not a simply supported beam. This is a cantilevered beam. So 5W L to the fourth over 384 EI and WL squared over 8, they won't work, okay? You need to find the appropriate formulas. And if you look here, I sort of showed you where to find them. The formulas are pretty straightforward. They're a little bit more involved than what we just did, but again, they're pretty plug and chug. So yeah. Any quick questions before we call it? All right. Well, if anybody has any questions, you can always just email me or send me a message in Teams or something like that. Nope. What page is IX table found on? What do you mean IX table? Are you talking about like where to find the IX values? That's just in table 1.1, like the very beginning of the manual where you look up the properties. You can also find the IX value in table 3.2 as well. They list the IX values in table 3.2. Not to look into the future too far ahead, but IX properties will also, there's another table that we'll look at later, but that's later. I'm not worried about that now. But you can find them in either table 1.1 or table 3.2. Anything else? All right. Well, I apologize for keeping everybody over a couple of minutes. Again, I'm sorry about my internet cutting out. I don't know if it's the weather or something like that. But it looks like we muscled through. That's all I have. Homework should be posted here at noon. And you got till next class period. That's all I got, everybody. Everybody be safe. We'll see you.